I'm live. Yay. Here we go. Lesson 17, basic factoring. What are you looking at right now? You're looking at actually what I call the guided notes. There's a link for it right down there. Right there we go. Right down there. You'll see a link to this file. It's a PDF file. You can print it out. It's got something like 4 pages to it because we've got 4 pages of lecture that I'm about to go through. I invite you to just sort of print it out and you can take your notes right on this thing. We also have, if you look down below, next below the guided notes, there's a link to the homework set. So this is the homework set that you actually have to turn in. It's only 2 pages or 2 sides of a piece of paper really. This goes to the D2L Dropbox. This is how you're getting your points for, well, for these homework assignments. Cool. Now, I suppose what we should do is we should get to the lecture. Let's just do that. Okay, here we go. What's going on? No, that should be off. There we go. Now we're ready. So this is that guided note sheet that I was just talking about. So we're going to do 2 kinds of factoring today. And the first kind of factoring is something that I call undistributing. It's kind of like distributing, except backwards. So you see that 10x plus 15? Can you imagine somebody might have distributed something to get that? The way you ask yourself what I would have to distribute is you first look at these 2 terms, the 10x and the 15, and you ask yourself, well, what have they got in common? Both the 10 and the 15 have a 5 in common. So you can think in terms of having a 5 distributing something. So 5 times what would give me a 10x? So you're kind of, thinking back to you're kind of going in reverse, right? We're not distributing, we're undistributing. 5 times what is 10x? Well, a 2x. 5 times a 2x would give me a 10x. And then a 5 times a what would give me the 15? Well, it's a plus 15, so I'm going to add, and it's 5 times 3 gives me the 15. So again, it looks like if you were to distribute this, 5 times 2x would give you the 10x, 5 times 3 would get you the 15. So it's undistributing, it's going backwards. So before the break, we were doing all kinds of like distributing and foiling, and that's multiplying things together, right? We used to multiply things together. Now we're going in exactly the opposite direction, breaking things apart. Breaking things apart into a set of factors, which means things that multiply together. So like factoring a 12 into 2 times 6 is one example. You could also factor 12 into 3 times 4. That's what factoring means. You're breaking something apart into things that multiply together. So here, again, when you see the 2 terms like this, you might ask yourself, what did I distribute? What did I have originally before I got to 10x plus 15? What did I have to distribute? And again, it's all about looking at the 10x and the 15 and asking what they have in common. Sometimes people will do it this way. They'll say, well, the 10x has a 5 in it. So really that's 5 times 2x. And then the 15 has a 5 in it. So really that's like a 5 times a 3. And so you'll notice that we have a factor of 5 in the first term. Come on, you. And then we have a factor of 5 again in the second term. Hence this phrase, common factors. The 5 is common to both terms. Remember what terms are. Terms are things that are separated by addition or subtraction. So I'll get used to this thing. So anyway, it's 10x plus 15. You have 2 terms there. So plus. So you have 2 terms, both terms contain a 5, and so what you do is you think in terms of undistributing the 5. Take the 5 out. If you take the 5 out of the first term, you're left with the 2x plus, and if you take the 5 out of the second term, you're left with a 3. So if you'd like to look at it that way, you can look at it that way. Mostly I'm just going to kind of do it the way I did it the first time. I'm just going to kind of undistribute just by thinking, what would I have to multiply to get 10x? Okay. Here's another example over here, 4x squared plus 12x. Well, you sniff at the terms. Again, I have 2 terms here. I have a 4x squared plus a 12x. Any kind of addition or subtraction is what separates terms. So you say, well, what do they both got in common? And I think you see the 4, right? Both of these terms have a 4 in them. 4 goes into 12. And notice also, I got x squared, I got x. Both of these terms have an x in them. They have at least one x. They have at least an x. So I'm going to pull out a 4 and an x. So this is what we mean by greatest common factor. That's a phrase you'll come across a lot. Greatest common factor, which just means take out everything you can. Take out everything you can get. I can take out a 4. I can also take out an x. So I'm going to take it all out. I'm going to take out a 4x. So 4x times what will give me 4x squared? Well, all I need is an x here. 4x times what will give me a plus 12x? Well, I need a plus, right? Plus times plus is plus. 4 times 3 would give me the 12. And then since I already have an x, I don't need another x. And so this is it. This is my answer right here. 4x times an x plus 3. I can put that in a nice big box. And again, if you ever have the least doubt in your mind whether you've got the right answer or not, you can just distribute real quick and make sure. 4x times x would give 4x squared. Yep, yep, yep. 4x times 3 would give 12x. Yep, yep, yep. So it's distributing, but backwards. Now, what do we got going on here? You see these two terms. Maybe I'll zoom in a little bit. You see these two terms. You got an 18, you got a 12. What goes into both 18 and 12? Hopefully you see a 2 right away because they're both even. 3 goes into both 12 and 18. Although actually 6 would work really well. 6. This is where knowing your times tables helps quite a bit. So 6 goes into both. Now what I'm going to do now is I'm going to advise that whenever we're starting with a negative, the first term is negative. We call that the lead term. The lead term is negative. Pull out a negative as well. So I'm not just pulling out a 6. I'm pulling out a negative 6. This is just kind of like good manners is what it is. So I pull out the negative 6, and then you have to ask yourself, negative 6 times what would give me a negative 18x? And the answer is 3 and x, like this, 3x. That would give me negative 18x. And then negative 6 times what would give me a positive 12? Well, I'd have to multiply a negative by a negative, and I'd have to multiply a 6 times a 2. So there we go. Negative 6 times 3x minus 2. And again, if you have the slightest doubt in your mind, you can always just quickly distribute it to make sure it comes out the same, and it does. Let's look at this one. I'll zoom in a little bit more. Let's look at this one. 3 terms. Wow, that's okay. You just look at all 3 terms and you say, what do they all have in common? Well, I see a 7, I see a 14, I see a 21. Those are all in our times 7 times tables, right? So I can pull out a 7 for sure. And again, because the lead term is negative, I'm actually going to pull out a negative 7. Again, it's just good manners. Actually, it makes life easier later when we do bigger problems. It will make our life easier to pull out the negative. So I'm going to pull out a negative 7. Negative 7 times what would give me this? I'd have to have an x squared. Negative 7 times what will give me a plus 14x? I'd have to multiply a negative by a negative to get a plus. I'd have to multiply a 7 times a 2, and I will need an x. There, 14x. Good. Finally, a negative 7 times a what will give me a negative 21. Well, a negative times a positive is a negative, and 7 times 3 is 21. Let's get rid of that. Beautiful. More examples. Ooh, getting bigger. What did I just do? I just did that one, right? Yep, okay. Here we go. Getting bigger. So again, we got 3 terms. They're kind of bigger looking terms, but that's okay. We got 3 terms. You look at the 14, the 21, the 35, and you say, what number goes into 14, 21, and 35? And hopefully you can think of a 7, right? 14 is in your 7s, 21 is in your 7s times table, so it's 35. But look also, every one of these terms has some x action in it. They all have x in it. So I'm going to pull out not just 7, but 7x. And now we ask ourselves, come on, Now we ask ourselves, 7x times what will give me a 14x cubed? Well, I'd have to double the 7. And x, I would have to multiply by x squared to get an x cubed. Okay. 7x times what is going to give me negative 21x squared? Well, I'd have to multiply by a negative to make it go negative. 7 times 3 gets the 21, and the x would have to be multiplying by another x to get the x squared. Okay, and then lastly, 7x times what is going to give me the plus 35x? Well, multiply by a positive. 7 times 5 will work. And notice I've already got the x. I don't need anything else. Just 7x times 5 is 35x. And there you have it. All nice and factored. Look at this one. You want to be a little bit careful with this one, actually. The approach is the same, of course. You're looking at all these numbers and you're saying, well, what goes into 12, 20, and 16? A 2 for sure. How about a 4? 4 will work. Anything bigger? 6? Nope. 8? Nope. Okay, 4. We're going to go with the 4. And then be careful about this part. You might be tempted to pull out an x. I mean, it looks awfully similar to this problem, doesn't it? But this term doesn't have an x. That's just a 16. There's no x there. So if you can't get an x out of all of them, then don't even pull an x out of any of them. Just don't. We're looking at all of the terms. What can I get from this term and this term and this term? I can get only a 4 from all of those terms. So 4 times what is going to give me the 12x cubed is the question here. And it's going to be 4 times 3x cubed. 4 times what is going to give me a 20x squared? I'll have to multiply by a 5x squared. And then finally, 4 times what is going to give me a negative 16? I'll need to multiply by a negative 4. There. And again, if you ever have the least doubt in your mind, you might have tripped in there somewhere, you want to check your answer, just distribute it back, because we've done distributing before. 4 times 3x cubed would give us the 12x cubed. 4 times the 5x squared would give us the 20x squared. And 4 times a negative 4 would give us a negative 16. So again, it's all the same distributing, just backwards. What's this got in it? Well, it's only 2 terms this time, but sure looks like there's a lot of junk to look at. Well, just look at each part separately. Look at the numbers. I got a 16, I got a 20. So there's a number that goes into both 16 and 20, and it's called 4. And then look at the x's. I got x squared, I got x. I can get x out of them, right? Look at the y's. I got y squared, I got y cubed. Well, I can get y squared out of them. Notice I'm going for the smaller exponent. I have a 2, I have a 3. I use the y squared. Why do I use the y squared? Because you can't factor y cubed from y squared. Y cubed times what is y squared? It doesn't really work so well. So you're always going with the smaller of your 2 exponents. So in the case of the y's, this is the 2. Use the 2. Okay. Back to our question. 4xy squared times what gives me the 16? Again, think about the number of the x and the y separately. The 4 has to be multiplied by a 4. The x will have to be multiplied by another x to get the x squared. And then the y squared doesn't have to multiply by anything. It's already a y squared. So that's done. Cool. 4xy squared times what is going to give me this stuff? Well, I'll need a plus 5. The x, I already have an x. I'm good on the x's. The y squared, though, I need a y cubed, so I'm going to have to actually multiply by a y here. I invite you to distribute that, make sure it works. It does. Okay, how many more of these I got? Okay, and then this is the last of this examples. Again, it's kind of big, kind of nasty. You might want to pause the video here and just bang this one out yourself, see if you get the same thing as me. Having unpaused. Okay, so I'm looking at these 2 terms. There's only 2 terms here, right? Because that's all a term. And then you come into a addition or subtraction. That means, oh, new term. And then this is the other term. So we've got two terms here. And so you look at the two terms and you say, what do they got in common? Looking at 24 and 32, you can go as big as an 8 there. Now, because my first term here is negative, I'm actually going to pull out negative 8. Okay, I like to do it that way. It's good manners, and it will make your life easier in later lessons if you learn to do this now. So I'm taking out the negative. Again, the lead term is negative. I'm taking out the negative. So I take out a negative 8. Wait a minute, I shouldn't have made the parentheses yet. Because, looking at the x's, what else can I get out? I got an x to the fifth, I got an x to the cubed. Remember, you go with the smaller exponent. I can get x cubed out of both of those. Look at the y. I got a y squared, I got a y to the fourth. Going with the smaller exponent, I can get y squared out of both of those terms. Okay, now's the part where I go like this. Negative 8x times what is going to give me all this? Well, the negative 8 has to multiply by 3. X cubed will have to multiply by x squared so that the exponents add up to x to the fifth. And then actually the y squared is done. So the first term is good. Yay. But now we have to ask ourselves, this thing times what will give us this stuff? So a negative 8 times a positive 4 will give me the negative 32. X cubed, I'm good on the x cubed. Y squared, y to the fourth. I'm going to need another y squared. Whoa, what'd you just do there? I'm going to need another y squared. Good, and it's all done. So it's just, you get some practice identifying common factors. That's all we're doing, is identifying common factors and pulling them all out. It's distributing, but backwards. It's undistributing. There's another basic pattern of factoring that I want to look at today because it comes up so often. And it's actually kind of a nice quick pattern once you get used to it. And it's called the difference of two squares pattern. Difference of two perfect squares. So you look at this one here and you say, hey, I got two terms. And it's a difference. So we're definitely off to a good start here. Are they squares? Well, yeah, they're squares. Look at them. So this is an A being squared, and this is a B being squared. We have a difference of two squares. Here's how this works. I'm going to actually just write it out this way. If you have something squared minus something squared, you take the first something and the second something, and you do this with it. That's your formula. That's your formula. So what the heck just happened? You had an A being squared. Notice where the A shows up, here and here. Then you had a B being squared. Notice where the B shows up, here and here. And we had subtraction. It's got to be subtraction, by the way. Probably should undo some of that. It's got to be subtraction, by the way. And because it's subtraction, I have a minus here and a plus here. And that is your basic pattern for a difference of two squares. It's a formula, is what it is. And what a formula is it's kind of it reminds you of the pattern. It's kind of reminds you what the dance steps are. This will work every time. You get something squared minus something squared. You're going to take those two things that are squared. You're going to take the squares off. You're going to minus them. You're going to plus them. So case in point, x squared minus 4. This works. That's certainly, x squared is certainly a square, right? But also, the 4 is basically a 2 squared. So I have a difference, which means subtraction, of two terms, squares, a difference of two squares. That's the pattern. So remember what we do, looking at the formula, we're supposed to take the things that are being squared, minus them, plus them. I got an x being squared, I got a 2 being squared, it's a difference of two squares. You just do this. I love this. Once you get used to it, it's like, you'll just eat these for breakfast. X minus 2x plus 2. That's the pattern. Now, if you're not quite knowing why you should believe me, then let me just prove it to you. You go like this. You FOIL this out, right? If you FOIL this out, x times x will give you an x squared. If you then go x times the 2 here, you'll get a plus 2x. And then you go minus 2 times the x here, and then you go minus 2 times the 2 here, right? So this is how you would FOIL it out. And then here is the neat effect. Those are supposed to be e's. Neat effect is that the plus 2x and the minus 2x are canceling. And so you just have x squared minus 4. Works like a charm. So that's why we have this effect of, you know, a minus and a plus, is to make one of these will be minus, one of these will be plus, and they'll cancel away. And it will work. So whenever you see a difference of 2 squares, this is what you're doing. Next, does that look like a difference of 2 squares? Well, it's a difference of 2 somethings, right? It's 2 terms being subtracted. Now, when you look at the 4x squared, you have to think in terms of the entire term. What times itself is a 4x squared? And the answer is 2x times itself is a 4x squared. Okay, so you have to think that way. Look at the 4x squared all together as one thing and say, what times itself gives me the 4x squared? 2x times itself gives me the 4x squared. Now on the 9, that's a 3 squared. So notice we've identified our little a and b thing, if you will. 2x squared minus 3 squared. And so the answer is going to be 2x minus 3, 2x plus 3. It's a really cool pattern. Here's another one. Again, look at the whole term here. Is that a square? What times itself is 9x squared? You have to think of the whole term. And it's a 3x times itself is a 9x squared. Minus, and now look at the 1. Is that a square? Yeah, it's a square. You can square 1 and get 1. I love that effect. So we have a difference of 2 squares. So you take the 3x and you take the 1 and you go 3x minus 1, 3x plus 1. And this works great. I hope you're having fun, because I'm having fun. This is great. What do we got here? Does that look like a difference of 2 squares? Well, it's a bunch of stuff. What times itself would give me a 49x squared? Well, 7 times 7 is 49. X times itself is x squared, so that's the square of 7x. What times itself is 81y squared? Well, I think a 9y will do that. So 9y times 9y is 81 squared, right? So I have 2 terms, yep. They're subtracted, yep. And they're squares, yep. So there's kind of like 3 criteria here. But if you match all 3 criteria, it's 2 terms, they're subtracted, and they're squares, then you can just follow the dance. 7x minus 9y, 7x plus 9y. Again, I invite you to just FOIL this out real quick. You'll get 7x times 7x is 49x squared. Then you'll get a plus 63xy, but then you'll get a minus 9 times 7 is 63xy, and those are going to cancel. That's the beauty of it. And then you get the minus 9y times the plus 9y, gives you the minus 81y squared. Differences are 2 squares. Don't leave home without them. All right, what's going on here? Well, the 25 looks like a 5 times a 5, so that's good. What would you square? What would you multiply by itself to get x to the 6th? Ask yourself this. X to some kind of power, that's not a 0, that's a circle, times x to some kind of power, and it's supposed to be the same power. You're supposed to multiply by the same thing. What do these 2 exponents have to be if multiplying gives me x to the 6th? And I think you'll believe me if I say they have to be 3's. Because 3 plus 3 is 6, right? Remember, when you multiply these x's times each other, you're gonna add your exponents, right? So the shortcut is basically cut exponent in half. Whenever you're asking yourself, what's the square root of x to the 6th, all you're gonna have to do is cut your exponent in half. X cubed times x cubed is x to the 6th. So what we've got then is x cubed is squared, minus 5 is squared. Therefore, we can factor this thing as x cubed minus 5, x cubed plus 5. So again, it's the x cubed and the 5 are being squared. So the x cubed goes here, here, the 5 goes here, here, and I minus them and I plus them. And it works like a charm. another page. Okay, x squared plus 9. Do you see two terms? I see two terms. Are they squares? Well, yeah, they are, right? 3 times 3 is 9. Is it a difference? Well, wait a minute. That's not a difference of two squares. That's a sum of two squares. So no, it's not a difference of two squares. So what am I going to do? I have to match all three criteria for these dance steps to work that we've been doing today. It's got to be two terms. It's got to be squares. It's got to be a difference. It's not a difference. Leave it alone. It does not factor. It does not factor. Now, I'll tell you what most people do is they kind of, the first time they see something like this is they say, well, we're doing with the difference of squares thing today, and usually we would minus them and plus them, except I'm trying to get a plus here, so I guess maybe I'll just do this, right? But be careful. If you're going to make a guess like that, at least test it. Make sure it works. Does this work? I'll put a question mark. Does this work? Well, if I go x times x, I'll get my x squared. Yeah. If I go x times 3, I'll get a 3x. If I go x times 3, I get a 3x again. And then I'll have my plus 9. So I've got the x squared, I've got the plus 9, but notice not a neat effect. These do not cancel. If you were to actually take x plus 3 times itself, you get x squared plus 6x plus 9. That ain't it. Which is why I'm saying if you have a sum of two squares, add. If you have a sum of two squares, leave it alone. It won't factor. Well, I suppose you might look for a common factor because that's what we were doing before. But a sum of squares does not factor the way a difference of squares does. Got to remember that. What's going on here? Difference of squares? Well, it's a difference. It's two terms. They're squares. Yes, this is going to work. What times itself is x to the fourth? Remember, you just have to cut the exponent in half. X squared, when you square it, gives you x to the fourth. You might remember there's a rule of a law of exponents that says when you have powers to powers like this, you would multiply the 2 times the 2 to get the 4. Whoops. How do you, well. So this really is x squared squared. If you were to multiply this by itself, you would add the 2 and 2 to get the 4, or again, the way you're looking at it here, you would multiply these two exponents to get the 4. Those are two separate laws of exponents. Anyway, that's an x squared being squared, minus, and that's a 4 being squared. So what we got here is we got at this, and we got at this, and we can minus them, and we can plus them, because this is a difference of two squares. So x squared minus 4, x squared plus 4. Cool. But hang on a second now, because, oh, that's too dark. Look at this thing. That's also a difference of two squares, right? That's one of the first ones we did actually in this lecture, or in this part of the lecture. So this is going to factor further. It itself is an x squared minus a 2 squared. So it's going to factor like this, x minus 2x plus 2. This is adding. It's a sum of two squares. We're not going to factor that. See previous example. And so that's our answer. We actually, this thing, x to the fourth minus 16, breaks up into 3 factors, 3 pieces that multiply, an x minus 2 times an x plus 2 times an x squared plus 4. And if you want to have yourself some fun, I invite you to multiply this out. If you were to multiply all of these out, you should get all kinds of terms canceling, and you'll end up with just this. Try it. Try multiplying. That'll be fun. You will, I promise, get x to the fourth minus 16. Whoops, what'd you do? Okay, 2 more examples. What do we got here? 12x squared minus 27. Do we have a difference of two terms? Yeah. Are they squares? Hey, you can't square anything and get 27. You can't square anything and get 12. No, they're not squares. So do we give up? Maybe, except remember we basically learned two kinds of factoring today in this lecture. And the first thing we learned was to try to pull out common factors. So actually, before we give up, because we don't see squares, we should ask ourselves, is there anything that I can pull out? 12 and 27, well, they don't have 2's, but they have 3's in them. I'm going to pull a 3 out. 3 times what would give me 12x squared? I would need a 4x squared. 3 times what would give me negative 27? I would need negative 9. So first you pull out the 3. That's the ticket. See, we can factor. And then lo and behold, now we got a difference of 2 squares right there. How about that? So we did have a difference of 2 squares. It was just hiding. So bring your 3 down, that's part of your answer, and then take the 4x squared minus 9, and you're taking square roots again, right? 2x minus 3, 2x plus 3. So the moral of this story, and this is going to be with us forever as we do all of these factoring problems. Whenever you're factoring, if you look at something and get stuck, always ask yourself, well, wait, can I pull anything out first? This actually happens quite a bit, where you pull something out and all of a sudden, oh, now I've got a difference of 2 squares, or something like that. So pull something out first always, and then you might have a difference of squares again. Or not again, but you will have one. Okay, last example. First thing I'm going to say is, hey, that's not standard form. STD period, not standard form. Question mark? Why wouldn't you have it in standard form? I don't know. Let's put it in standard form then. Standard form is what? That's where you have the biggest exponents first. You put the x's first and the constants second, or if you have a bunch of x terms, you go in order from highest exponent down to lowest exponent. So I'm just swapping those two terms around. So the negative 2x squared comes to the front, and then the 18 comes over to here. Okay, that was fun. Certainly not looking at a difference of 2 squares right now, but I really should try to pull something out, right? So you're looking at the 2 and you're looking at the 18 and you're saying, I know I can get a 2 out of those. And then also, because the lead term is negative, there's this thing that I'm advising, recommending, I might as well say requiring, pull the negative 2 out. Pull out a negative as well. So when you pull a negative 2 out, negative 2 times what is going to give me this? Well, all I need is x to the 6th. Negative 2 times what is going to give me 18? Negative times negative is positive. 2 times 9 is 18. Okay, cool. Let's get rid of some of this stuff. So I put it in standard form first. Good idea. I pulled out the 2. I pulled out the negative while I was at it. And now the thing left to do is ask ourselves if that's a difference of squares. Difference of squares? And it sure is. I think we had x to the 6th earlier, didn't we? Didn't we? Yeah, we did. Remember, we talked ourselves into this, that the square root of x to the 6th is x to the cubed. You just have to cut the exponent in half. So that's back. Here we are again. I get x to the 6th again. So this really is a difference of squares. X to the 6th square root is x cubed, and the 9 square root is 3. So I got an x cubed minus 3, and I get an x cubed plus 3. And that's the end of the lecture. Ooh. Anybody want to play Dotso? Okay, I get carried away. Okay, so anyway, that's our lecture on the two basic forms of factoring: pulling out common factors, differences of squares. Hope you have fun on your homework. And by the way, oh, look at me be clever. Ha! I'm over here, see? So by the way, down there where I pointed out that you have the guided note and the homework, you can also just leave questions. You got a question? This would be great if you say like, oh, I have a question at the 12-minute and 30-second mark. Just say, question, 12 minutes, 30 seconds. What did you say? Or, are you sure you can do that? Or, can't I just do this? Or whatever question you might have, just leave it right there in the YouTube comments. And I'll be checking in at least 4 times a week when the semester's in progress anyway. And this should be fun. Okay, so how do I turn this off? I should learn that. How do you turn this off?